Hi.
How's your cat doing?
Good.
What was her name?
Chen Chen.
Chen Chen.
Yes.
You said, what does it mean in English?
Uh. None.
Sorry, what?
No meaning.
Chen Chen. Oh my God, I love cats a lot. I have an Instagram account. I only follow the pages which they have cats. I love baby cats. Oh my God, they are so cute. Okay, now, while while Gloria is looking for the Chen Chen meaning, let's start the lesson today, which is the most beautiful lesson we are gonna have. Okay, today, guys, we are gonna talk about yesterday that we talked about a very interesting function, which is the sine of the x. And we talked about the inverse of the sine of the x, and we reviewed some examples. And also we discovered one identity, that it was the composition of the sine x with its inverse, which is always equals to x, correct? But do you have any questions now from yesterday's lesson?
No.
Okay, because this weekend you are gonna have homework for the inverse of trigonometric function. And if you have any questions, please don't be shy. Ask it today, because you are gonna do some problems tomorrow about the inverse of trigonometric function. Then that's crucial to, don't be shy. Ask the questions in case if they arises. Okay, and now. Let me pin the video here. And let's start. Okay, guys, now the thing that we want to do right now is this. We starts with another type of inverse of trigonometric function. This time we start by the f of x, which is the cosine of the x. We start by the f of x, which is cosine of the x. You remember from the things that we learned yesterday, we saw that when you want to talk about the inverse of a function, which is essentially the main lesson, the plan for today, we drive the inverse of the cosine of the x and try to investigate some properties of this function. Based on the things that we learned yesterday, how to drive the inverse of the trigonometric function, we saw that we follow again as before 4 steps. For step number 1 that we learned yesterday was that we call that step number 1. We change f of x to y. We call that y equals to cosine of the x. Then as you learned it from, I should say, beginning of the session, we said that we talk about step number 2. Step number 2 is gonna be walking from the left towards the right. And wherever we see, I should say, y, rename it to the x, and wherever we see x, rename it to the y, then we end up with this expression, x equals to cosine of the y. And for step number 3, we saw that we can, the logic behind that, it should be clear today. After the session today, we call that we can, in order to isolate the y on one side of the equation with the power 1 and coefficient 1, that's what we did before in step number 3, we take cosine inverse from both sides. You get to understand why I'm doing that at the end of the session, but you can see that the step number 3 becomes very easy. You can change it to this notation. Cosine inverse of the x equals to y. And for step number 4, which we did before, we said that, okay, while you're at that stage, it depends to us. We can write y, replace y with f inverse. of the x, which becomes what? Becomes cosine inverse of the x. That's going to be step number 4. That's essentially these 4 steps that I took. These are the same thing that we did it, I should say, many days ago while we talked about the inverse of a function. And I didn't add anything to that. But also, you see that we can write this function in a different way. We can also write inverse of the cosine. We can write it as equals to what? Equals to arc cosine of the x. And remember, when I was at your age, some people used to write arc with small a, some people write it with the letter capital A, and I was confused if arc cosine of the x with the smaller capital letter A are going to be the same. But I'm going to tell you now that they are essentially the same. Arc cosine of the x, if A is small or capital, essentially it's going to be the same thing. It's going to be exactly the same thing. Okay, and now that's essentially the inverse of the cosine function. It's going to be page number 1. Any questions, guys?
No.
No? Then what we did here, wherever you see in future with the trigonometric function, it's very easy to find the inverse because in the past, we had to take these 4 steps for the functions depending on how they varied in the field to find the inverse. But for the cosine of the function, it's very easy. Don't follow these 4 steps. When you are the cosine of the x, you know for sure, that the inverse is arc cosine of the x. You do not need to follow these steps to find it. You are given cosine of the x, the inverse is arc cosine of the x. Then it's going to be very easy. Okay, any questions from Philip and Gloria?
No.
No?
No.
And now, I'm just going to do as what I did before to draw a table in order to just make some comparisons of these functions together before we move on. I'm going to plot these 2 charts. This one is going to be the function, it's going to be the domain, and it's going to be the range. It's going to be the function, it's going to be the domain, and it's going to be the range. Okay. We start with this one. We say it starts with the function, which is going to be the cosine of the x. Okay. Guys, what is the domain of the cosine of the x? I'm going to fill out this chart with your help, guys, to tell me what is the domain of cosine of the x and what is the range of the cosine of the x. What is the domain of the cosine of the x?
All real number.
All real numbers. How about Philip and Gloria?
All real number.
All real numbers. Yes, Gloria?
Yes.
Yeah. But you remember also from the thing which we did a couple of weeks ago, that we said that if we have a function, for example, this is f of x, which we say that, guys, by the way, you see clearly what I'm writing? I mean, the light is fine, the color of the pen is good.
Yes.
Everything is clear for everyone?
Yes.
Awesome. We saw that a couple of days ago that when we have a function, we call that the cosine. And let's call the cosine has an argument, which that argument is g of x. We saw previously, when you want to define the domain of the cosine of the g of x, you find the domain of the g of x. That's what we did. We said that then the domain of, cosine of g of x essentially becomes the domain of what? The domain of, let's say, g of x. For example, based on the thing that we saw, as an example, we saw that the domain of, let's say, for example, the cosine of the square root of the x, it becomes what? You go to the domain of the square root of the x, because you see, whatever is the argument of the cosine, that argument should be valid and legitimate. Then if you have a square root of the x, it means that the square root of the x should not be negative inside the square root, which it means that the domain is going to be all the real numbers belonging to the R. However, x has to be greater or equal than 0. And that's a kind of a review of the thing which we did for the domain of the R. However, then if you have the cosine of the x, you focus your attention for the domain of the x itself. And if you look at even the plot of y equals to x, you see x can take any real number possible in the real space. But for the domain, when we want to talk about the inverse of it, as you saw yesterday, we have to shorten, truncate. Truncate means shorten, to make something smaller, the subspace of the R, because you see the huge benefit of doing that. Because in the inverse side, as you saw yesterday, you are only need to find only one angle in the inverse function. Otherwise, if you're looking for the domain of the cosine x as the all real numbers, you can have infinite number of the answers, because the function is, as you have seen, it has a repeating pattern. Then I come here for the cosine of the x. I choose a very small domain of the function, like the sine that we did yesterday. For the sine, we truncated our domain into from minus pi over 2 to plus pi over 2, but for the cosine, we focus between 0 to pi. That's going to be the domain of the cosine of the x. It is true that the all real numbers, it can be the domain, but for the cosine, we focus on this. And now, thus it's going to be this one. But what is going to be the range?
-1 to 1.
That's so true. It becomes -1 to +1. Because you know that the function f of x, which is cosine of the g of x, regardless that what is g of x, f of x is always confined to oscillate, to be confined between -1 and +1. Square root of the x, g of x can be any form, but the range is going to be always this. For example, for the cosine of the square root of the x, although the domain is all the positive x, but the domain, the range can be what? Can be between -1 to +1. Okay. And now, that's any questions, guys, so far?
No.
No questions yet? Okay. Now we go to the inverse of the cosine. Cosine inverse of the x. For the cosine inverse of the x, what is going to happen now? I just want to throw your attention from the thing that we did before, that we said what? We said that it was a lesson yesterday, when we have a function and when we have its inverse function, we have a very interesting property that the domain of one becomes the range of the other, and the range of one becomes the domain of the other. They are crossing itself in terms of the domain and the structure. Then it means that for the cosine inverse of the x, its domain becomes the range of this function, which it means that the domain of this one becomes between -1 to +1. Then it means that, guys, if with the cosine of the g of x, you said that you have the freedom to focus your attention to the g of x, to find the domain of the g of x. But for the cosine inverse of that function, you do not have that freedom to say, okay, the domain can be anything. The domain has to necessarily be confined in this range. For example, you cannot have, let's say, cosine inverse of -3, as we had a similar case with the sine yesterday. Cosine inverse of -3, -3 is not in that range, in that domain. Then we said that cosine inverse of -3 is, sorry, nonsense. It's not existent. And also at the same time, we said that the domain of this function becomes what? The range of the inverse, which it means that the domain becomes this one, becomes 0 and pi. It becomes here, and now it becomes the range of this function. Okay. However, I have to tell you guys, for these two properties which we have written, we are going to focus our attention right now, because these ones are going to be very crucial when you evaluate your inverse trigonometric function. Your evaluation should always adhere to this range. I'll give you an example right now to see what do I mean. Any questions, guys, so far?
No.
Everything is clear?
Yes.
Okay, give me 1 second. I bring a glass of water for myself. I should be back so soon then. Okay, and now let's give some examples to see what do I mean. Okay, the first example which I have for you is this. It's a very easy thing. Imagine I'm asking you about this, that I'm telling you the cosine inverse of, let's say, square root of 2 divided by 2. What is that? Let me get this one. Essentially, in order to answer that question, I have a very interesting example to tell you. You can, essentially, in order to answer that question, you can come to the second type of the question to ask yourself, what angles cosine becomes square root of 2 over 2? And now it's much easier to find this one. And what's the relationship between these two things which I have drawn here? Look at this. You ask yourself in this context that what is, let's say, the cosine inverse of square root of 2 over 2? Then it's the same thing if you ask yourself what angles cosine becomes square root of 2 over 2. These two guys, these two expressions, essentially are just like two sides of one coin. Have you seen loonies in Toronto? By loonie, I mean a coin, a $2 coin in Canada. Have you seen that? Yes, Rose, Philip, Gloria?
No.
No? Have you seen the $5 note?
$5 note.
$5.
Oh, yeah.
Yes? Imagine that you are going to a grocery store, you want to buy something, buy cookie or candy. Does it make a difference to pay your $5 from this side or from the other side?
No.
They are the same, they have the same value, huh?
Yes.
Or even with the coins, you have a $2 coin, you buy something, it doesn't matter, this side of the coin or that side of the coin, they have the same value. The story is going to be essentially like this, that if you ask yourself this question, it essentially is to ask yourself this question. They are essentially the same value. If I ask myself, what angles cosine becomes the square root of 2 over 2, what is the angle?
Pi over 4.
That's right, 45 degrees or pi over 4. The same answer is going to be this, pi over 4. You see then these two expressions, the cosine and the inverse of the cosine, they are essentially like two sides of a coin. They have no difference. The value of this essentially is the value of this. It doesn't mean that if you pay $5 from this side, it's worth $2, and from the other side, it's $5. From both sides, it's $5. And that's why I say that these two expressions should remind you of two same expressions, two same quantity. Okay, now before I move on, I'm going to give you one example. I'm going to give you one example, and this example is going to be this. Actually, two examples. The first example which I'm going to have for you is this. What is the cosine inverse of pi? Oh, guys, by the way, before we move on to that section, I just get that example to explain this, that look at the arguments. For the cosine inverse, we said that the argument of it has to be minus 1 and plus 1. And you see that the square root of 2 divided by 2 is in that range, correct? Then that makes sense. And also you see its range, pi over 4, is inside that range, which is between 0 and pi. If you get something with 2 pi, it means that it's wrong. It has to be between 0 and pi. That was the reason I explained this chart for you, and I gave you that example. That I show you that, okay, for the inverse of a cosine, you have to make sure that the argument should be confined between minus 1 and plus 1, and the range, which is the answer, should be within that range from 0 to pi. Otherwise, it's wrong. Everyone is fine now?
Yes.
If that's okay, please answer this question. What is the cosine inverse of the pi? Any answer now? Any answers? Any answers, guys?
No.
Gloria, Philip, Rose?
No.
Philip and Rose? Rose?
Yes.
What is the answer?
No answer.
No answer. Great. Why there is no answer? Because cosine inverse of the pi is what? Pi is around 3.14, correct? 3.141519 goes on. But whatever is that going to be, you see that 3.14 is outside of the domain, which it has to be between -1 and +1. Then you come here, you see, okay, cosine inverse of the pi. Then it means that, oh my God, there should be no answer. There should be no logic behind this expression. It means that there is no answer for this expression. Okay? And now, we just go to the last example for you. This is going to be this one. We say that the cosine inverse of, let's say, cosine inverse of, let's say, minus guys, please give almost, I think 5 minutes should be fine. Then try to see if we can come with an idea of what is this function is going to be. Cosine inverse of minus square root of 3 divided by 2. I think 5 minutes should be a reasonable time because this one, it needs one more step compared to the other things which we have done. And please let me know, guys. And essentially know that in order to answer that question, you can answer this question for yourself instead. That what angles cosine is minus root of 3 divided by 2? Because you know both of them are the two sides of the same coin.
It's 150 degrees.
150 degrees. Tell me that in radians because I do not have the answer in degrees then.
Degrees.
How about Gloria and Philip? I give you 1 more minute, then I just do that for you then. I think, Rose, you are almost correct, I think. I just need to, you said 150, huh?
5 pi over 6.
That's correct. Fantastic. And I give 1 more minute to Philip and Gloria, then we just solve it together. Okay, Philip and Gloria, are you done? Yes? Philip and Gloria, are you there still or no?
Yes.
Yes.
You are still there. Okay, in order to answer that question, I just want to draw back to review some concepts that we had. And as usual, we go to these concepts that we just talked about that before. And that concept was this. It's a popular unit circle, which we have worked with that many times so far in our study in the trigonometry. I'm going to draw the unit circle. I'm sure you do not see that circle because the camera maybe do not show that circle, which is in pencil. Do you see that circle, guys, or no? Am I right? You do not see that circle, huh?
I can see it.
Oh, okay, that's good. Okay, it's going to be the x-axis, it's going to be the y-axis, and now we have this one. Guys, look at this. The crucial thing, Gloria and Philip, please listen to this very carefully because this is very important. We are going to review that again. Imagine that I have one angle. I make it, let's say, for this one, I just find a point here on the circle, at the circumference of the circle, and I call that point X. And I decide that this point, let's say, becomes what? Becomes, let's say, let's call that alpha. Do that in a very general way. Yesterday, we saw that if we have that case, in order to find in the unit circle the cosine of the alpha, the only thing that we have to do is to project it on what? On the x-axis, correct? Then whatever you read along the x-axis, it gives you what? It gives you the cosine of the angle, because based on the things which you learned a couple of weeks ago, the cosine ratio of an angle is essentially the ratio of the x coordinate of the point, which is rotating along the circumference of the unit circle, divided by the radius of that circle. And if the radius is going to be 1, because that's why we call that unit circle, it means that the circle is unit in length, then r is going to be 1. Then the ratio of x divided by r, which is the ratio of x divided by 1, becomes x. Then you see that on the unit circle, the cosine of any angle, which is, I should say, collected by the x rotating along that, is the x coordinate of that point. Okay. Now, imagine that now x is positive now because it's the angle is in the first quadrant and the x is positive. Imagine that I'm just going to make the same x, but the negative x. Why I'm doing this? Because the cosine of the angle, which I'm talking about it right now, I'm asking myself, what is the angle? That its cosine is minus square root of 3 divided by 2. Then it means that the angle is in such a way, the x has been rotated in such a way, either counterclockwise or clockwise, that the point is on what? Either the second quadrant or the third quadrant, that its projection of that point along the x-axis becomes what? Becomes minus, correct? Then the x is going to be this. I have two things to do in order to find that point. Either I can just come here and the point which is, it measures to the origin, because you see that this is going to be the origin here, you see? And the length from origin to this side, which is x, it can be imagined that, for example, 1 over 2, anything. Or, for example, the same thing. Imagine that's the same thing. If x here is square root of 3 divided by 2. Correct, Philip and Gloria? But with the positive sign, this one is going to be a minus the square root of 3 divided by 2. Until this point. In order to find the angle, I have to be very precise. Let me measure that in with centers, because otherwise the geometry is not a very good one. It's going to be from 1 to 3.4. Okay, the point should have been here. My x was a little bigger. Then what I'm going to do, I'm just going to, okay, make a trajectory on the circle to find these 2 points on the circumference of my unit circle, which it means that if I choose my angle in a way that either this angle or, let me choose a different color, or this angle they have the same cosine value. Correct, Rose?
Yes.
By this angle, by the blue, I mean this. Or by the other one, I mean this angle. Okay, and now, okay, what is this angle, guys? The blue one. I call that alpha 2. I call it alpha prime. What is alpha prime?
Pi minus alpha.
That's so true. Alpha prime, it's essentially what? Pi, which is 180, means Gloria and Philip, look at that. From here all the way to here, you are moving from 0 to pi. Is it correct? You're moving from 0 to pi. Then here, pi, you just want to take this one because you see that this angle is also alpha. Then becomes pi minus alpha is essentially this angle from here all the way there. And call this one alpha double prime. How much is alpha double prime?
Pi plus alpha.
That's so true. Pi plus alpha. Now, then guys, you see that if my cosine, which is positive, is square root of 3 divided by 2, we know that pi, how much is that alpha? Alpha then, Rose? If the cosine is square root of 3 divided by 2.
Is pi over 6.
That's so true, pi over 6. Then Gloria and Philip, you see that if x is only positive, which it means that the x is going to be here, which it means that it is square root of 3 over 2, the alpha is one of those popular friendly reference angles. We talked about that many sessions ago, that it's going to be pi over 6. Then if alpha is pi over 6, then I have 2 other alpha. I found 2 other alpha, alpha prime and alpha double prime, which their cosine becomes minus x, the way which geometrically I plotted here for you. Then how much does possible alpha? It becomes pi minus pi over 6 becomes how much? Guys, pi minus pi over 6 becomes 5 pi over 6. Do you see this one, although this is a little bit small in font? Do you see that, guys?
Yes.
Awesome. And also the second thing, alpha double prime becomes what? becomes pi plus pi over 6. Because pi over 6, that's our reference angle, becomes what? 7 times pi over 6. Then you will see that, guys, very easily, that I have now two angles that its cosine becomes minus square root of 3 divided by 2. Because you see that these angles, the red one, which measures this angle, it goes to minus x, and x is the square root of 3 divided by 2. And you see also the other angle, which is the blue one, which is pi over 6. This is this angle, which they both collect the same value on the x-axis. And now, the question is that, then I have, in order to fill out this box, I have two values. One, 5 pi divided by 6. Let me collect this one. And also, I have this one. Then I have two angles. But I have one box. Then it means that one of the angles is redundant. I do not need the other angle. Which one you think is going to be the best one? Between 5 pi divided by 6 or 7 pi divided by 6?
5 pi divided by 6.
Why that one, Rose?
Because it's between 0 and pi.
Fantastic. Gloria and Philip, we have two options, but in order to answer which one is best, we move to this one. We ask ourselves essentially, the answer which I have, which is going to be the range, is it between 0 and pi? Because initially I noticed that minus the square root of 3 divided by 2, which is the domain, is between minus and 1 and 1. I'm satisfied with that. But the range, it has to be between 0 and pi. Then it means that these answers has to be between 0 and pi. Which one between 0 and pi? In order to, maybe it's tricky, you don't know which one is between 0 and pi. In order to do that, pi represents 3.14. Put pi here, 3.14, multiply to 5 divided by 6. You see that this is less than 3.4. But this one, put pi 3.14, multiplied it to the 7 divided by 6. You see the answer is bigger than 3.14, which is the outer limit of this function. Then as a result, you put this aside and you see that this answer is not going to be acceptable. Then this answer is going to be the one which is acceptable. Then you say that the answer is going to be 5 pi divided by 6 and also 5 pi divided by 6. Beautiful, guys, huh? Good question. Interesting question. Guys, any questions? Any need for clarification?
No.
Everyone is fine?
Yes.
How about Gloria and Philip?
Yes.
Guys, please don't be shy to ask questions because you may have the same thing on your test. Then maybe the exact same thing. Then make sure that you get it. You got it, Philip and Gloria?
Mm-hmm.
Fantastic.
Yes.
How about you, Gloria?
Yes.
Are you sure, Gloria?
Yes.
Okay. How about Shen Shen? Did she got the same thing?
Yes.
What's she doing now? Sleeping.
Sleeping.
I love cats very much. Okay. Now, before we move on, what time is it now? you have almost 3 minutes. Before we go, I'm just gonna show you the plot for, because one of the things, maybe, no, it's good to just show you that the plot. I'm gonna share my screen with you to show the plots of the functions itself, because you remember that, I have the plot actually ready. You remember that, guys, when we talked about the inverse function, we said that the inverse function, they have an interesting property that the y equals to x, it becomes the line of symmetry for these plots, for these functions, the inverse of a function in itself. Okay, now, everyone has my screen?
Yes.
Yeah? Look at this one, guys. I have the first function being plotted, which is f of x equals to arc cosine of the x. And you see this function. Take a closer look. You see the domain of the function, which will mean that whatever is along the x is between 1 and -1. And the domain of the function, you see, sorry, the range of the function, whatever is along the y, it's from 0 goes to this point, pi. That's what we talked about that on the chart. You see that clearly? The domain between -1 to 1, the range is between 0 to pi. But look at this. That's my function. The blue one is what? The blue one is, let's say, between, the blue one is a cosine of the x. Guys, I do not subsegment the function because you see the whole function. But remember that if I just plot y equals to x as a line of symmetry, you look at these two parts, the red one and the blue one, which is moving from here to there. You see, from here, which is just, this is the hand, goes all the way to there. You see the blue one from here to there? It's between pi to -1, going to 0 to 1. You see, this is exactly the image of this one, the green one, from here to there. You see that? Yeah?
Yes.
Then you see that the y equals to x, it becomes the line of the symmetry for that plot. Is that clear for everyone?
Yes.
Yeah? You do not look at the whole blue line, just look at it from here. From here, that it moves all the way to here. It's as if, with respect to the y equals to x, that they are the mirror image. This one is the, for example, if this is the head, this one is also the head on that mirror then. Any questions, guys?
No.
Philip and Gloria?
No.
No.
And Chen Chen?
No.
No question from Chen Chen? Okay.
Yeah.
Guys, if you have no questions, right now, you have the right timing to take the break. Please take 15 minutes break, come back by 12:26. We continue from then now. Okay.
Yes.
Enjoy your break. See you in 15 minutes. Come back, everyone.
Yes.
Good that the Gloria is back. How about Philip and Rose?
Yes.
How about Philip?
Yes.
Great. Oh, hold on a second. Okay. Now, just we are going to just start today with a very interesting, I should say, concepts. But before we do that, I'm going to remind you of the third property that I was planning to just do that before we just go for the break, but never is late. I'm going to do that now, review that identity, then we move on to do some interesting stuff. Okay, now, one of the things that we learned before, and we saw that also in the sine and inverse of the sine function, was that when you just make a composite function of a function with its inverse, you get always x. What do I mean? I mean that we just saw before that f minus x o f of x, the composite function, if we can call that, equals to x. And at the same time, we saw that the same thing is valid if we say that f of x, the composite of f of inverse of the x, is always equals to x. You remember that we talked about that many weeks ago, and we did lots of practice examples on this. Also, we used that yesterday to come to these identities. This identity, which we can derive it of the cosine inverse of the cosine of the x, which should necessarily go to x. And also, we come derive this one, that the cosine of cosine inverse of the x, it is going to be also the x. And that's the thing that we easily deduce it from the basic properties of the composition of a function with its inverse function. That always when you make this composition, they are going to be the same thing. They are going to be giving you the x. But you can also come to this very general conclusion that although from this, that the cosine inverse of the cosine of g of x, this is not x anymore. It also is going to be g of x itself. And the same thing for that one. These are some, I should say, basic identities, which is easily and readily taken and deduced from the function composition, which is inverse. However, the lesson that we're going to do today is essentially, it's a kind of a deviation from it. We are going to find some complex models that we have, for example, cosine inverse of the sine function, which we will see that they are not going to be of the same nature. Look at this one. For this one, it's always very easy to find the g of x because we see that the cosine inverse and the cosine, they are coming from the same nature. Then the composition of them, it always gives you the g of x. G of x in its the easy form becomes the x itself. But in order we find those identities, which is more interesting to work with that. Before that, I'm just going to start with one very easy example. Then from that easy example, we move on to the more complex ones. But any questions, guys, from this identity here? Any questions for this page?
No.
No, everyone is fine. Gloria and Philip also.
Yes.
Gloria are fine.
Yes.
Philip, you're
Yes.
fine. Awesome. And Rose also said that she's fine. Then the thing which we do is that we move on. We move on with a very interesting example. And that example is going to be this. I'm just going to give you the example that I'm just going to ask you to find the sine inverse of cosine of, let's say, call that pi over 3. Okay. That's the plan that we want to do. And that's the task that we have it for now. Everyone can see clearly what I have written?
Yes.
Awesome, great. Then let me put that very interesting box. I love to use rulers. If I do not have any straight line as it should be, it just distracts me. That's I'm right using ruler a lot. Okay. Guys, do you have any idea, any strategy to solve this problem? It's a little bit different from the other one because we see that sine inverse of the cosine. Then these inverse function with the forward function, they are not from the same nature. For example, that's a girl and that's a boy. They are not from the same nature. Then I cannot just come right away to write that. It becomes, let's say, it becomes pi over 3. Because I know that based on the thing that I learned yesterday, we talked about this, that we saw that the sine inverse of the sine of pi over 3 becomes how much, guys?
Pi over 3.
That's so true, becomes pi over 3. Why these things happens? Because this is the composite functions of the same nature. You see sine, you see inverse of the sine. But here it's different. We have sine inverse and we have cosine. Then I cannot write here p over 3 because it doesn't make sense. I didn't make a composition of cosine with its inverse. I made the composition of the cosine with the inverse of the sine, which it means that I cannot use the basic identity to say, okay, whatever is there, it comes out. But what's the plan? I call this plan, I called it onion. You know what is an onion, guys? You have it for your lunch, dinner, or when you do cooking, huh?
Yes.
It becomes, these type of functions can be, like the onion, get lots of layers. You see, when you cut the onion, you see that it comes lots of layers inside and you go to the core of the onion. You have seen that, huh? If you have done cooking. Then this, I call that the onions. I call this one the function which is inside. I call that the inner function, or let's say the core function, or inner function, core, C-O-R-E, which it means that this is the inner one. This is just the core of the onion. And I call the sine inverse as what? You know what is that called? If that's the core. I call that outer function. It's O-U-T-R-T-E-R. You have the onion, that's the core, and that's the outer layer that you peel this off in your cooking. The strategy, guys, is that it doesn't matter how many layers you have. Maybe you have the sine inverse of the tangent inverse of the cosine of pi over 3. I added one more layer. It doesn't matter. The principle is the same. You always go to the core function, the function which is just the written inside of the whole layers, inside the core of the onion. You take this out and you follow, you start from there. It means that I take, this example is very easy. You see the benefit which I'm talking about on the next example. Then I take the inner function, which is going to be the cosine of pi over 3. What is the cosine of pi over 3, guys?
One over 2.
That's right, 1 over 2. I think it's good that you write these trigonometric ratios of the reference angles, which is pi over 6, pi over 4 and pi over 3 on a piece of paper and paste it on your desktop. When you have a class, when these things comes up, you take a look there and give the answers. Yes, Gloria, Philip, and Rose?
Yes.
Yes, thanks, Rose. And now, what is that, guys? Then the problem of the core function now is resolved. I take a look inside of the core function, then I know that the cosine of pi over 3 becomes 1 over 2. Then the problem is what? The problem is now reduced to a very basic one, and it becomes what? It becomes sine inverse of what? Of 1 over 2. Right? Because the core is 1 over 2, and it becomes sine inverse of 1 over 2. And now I have to solve this. But I stop. I take a pause. I take a deep breath to analyze the domain of the function which comes in front of the sine inverse. What do I mean? I bring my chart. I take a look at it, and I see the domain has to be between -1 and +1. That's how it has to be. And I check that 1 over 2 is exactly in that interval of -1 and +1. Then it means that I can continue. If it was out of that bounded region, it means that I have to stop. I cannot continue. The street is closed. I cannot go further. But what is the sine inverse of 1 over 2? What does it mean?
Over 6.
Sorry, what?
Pi over 6.
That's fantastic. Thanks, Rose. It means essentially what? It means essentially you are going to answer this question. This equivalent question. That what is the sine of angle what is the angle that its sine is 1 over 2? And what was that, Rose?
Pi over 6.
That's right, thank you. It becomes pi over 6. And as you learned, they are the same side of the coin. These two should be the same thing. Then I go back to the original problem which I had. The sine inverse of cosine of pi over 3, it has to be what? Pi over 6. Any questions, guys?
No.
Everyone is fine?
Yes.
Okay. How about Philippe and Gloria?
Yes.
Yes, Gloria? How about
Yes.
Philip? Yes?
Yes.
Awesome. Then you see that with this very basic example, we developed a kind of a strategy. For these mixed models, I call these functions, I should say, I call them mixed models because it becomes like the mix of forward trigonometric function and backward trigonometric function, and you mix it together to create a new function. That's why I call that mixed models. And we develop a kind of an idea of the onion rule. We cut the onion, we start from the core of the onion, then we go outwards. And that's the rule which we developed here. I call that onion. It's not in any book, that's the name which I have given that to it. In case if you want to Google it, there is nothing like that. Okay, now we go to some more interesting example. This example is very interesting. And that's why I think probably it takes the rest of the day from us. What time is it now? Guys, what time is it?
12:42.
Oh, really? Oh, my goodness. We have less than half an hour. That's going to take the rest of the class, this example. We start with this example. I said that the mixed model is going to be now different. Becomes a new function. Becomes the secant. Let me write it here. I'm going to give you a function. I call that function f of x, a single variable function, becomes the secant of, you remember the secant is the inverse of the cosine, the secant of inverse of the sine of x divided by 4. Okay, now we have this function to analyze. This function is a very interesting looking function, huh? It's a mixed model because this function is the secant sine inverse of x over 4. I have x, I have x. It means that the function is a single variable function. How to evaluate this function? Guys, please listen to that. That's, I have to say, this is the most important thing you are going to learn this term. Everyone, listen carefully. Even Chen Chen. Okay, now, what is the strategy, guys? We have these mixed models of the forward function and its backward function, which is the inverse. The rule is the onion rule. What was the onion rule? The onion rule was that cut the onion, just go deep inside, find the core of the function. Which one is the core function? This function, huh? It is the core function. That's the core function. And now, you have a knife when you're cooking. Take the knife inside, peel this core from this, I should say, inside the onion, remove it. When you remove it, you have it on your chopping card. What is your chopping card here? It's going to be the sine inverse of what? X divided by 4. I'm just going to name it because if you have that core of the onion on the plate, you have to name it something. For example, Gloria asked Rose, Rose, what is that inside the plate? She doesn't identify this core of the onion first. Then that's why Rose gives it a name. The name which Rose gives to this core, it can be anything, but let's call that alpha, a Greek letter, alpha. That's what we did so far. And now, I start from here, from the core. I remember something. I remember that if sine inverse of x over 4, if I get the sine, composite that with the sine, I can remove x over 4, right? Because that was the identity which we learned. I'm going to write this identity inside a kind of the table. It means that we borrow that method now. And the thing was this. We said that the sine, it's from yesterday's lesson, sine inverse of sine of the x is equal to what? It's equal to x. That's the thing that we learned it yesterday. And now, or also the same thing, I should have written this, the other thing, that also the same thing, that the sine of sine inverse of the x equals to x. This is more relevant here. I mistakenly read this one, but this one is more relevant. Then I see that if I take the sine from both sides, I can take x out there. What does it mean? It means that I write sine of sine inverse of x divided by 4 should equal to what? The sine of alpha. You see that? I take sine from both sides of the equation. It means that if A equals to B, under some conditions, sine of A should equal to sine of B. Is it clear, guys, everyone, so far?
Yes.
Yeah? And now what's happened there, I'm just going to use this identity, the identity which is there, to come to this conclusion that the sine of sine inverse of 1, sine inverse of x over 4, you see these two functions, guys, are from the same nature. That's right. They are representing the same type of functions. Then I can use this identity. Then I write at the end that x divided by 4 should equal to the right side, which is going to be the sine of alpha. Any questions, guys, so far? Is it clear?
Yes.
Great. How about Philip and Gloria?
Yes.
Good. Philip?
Yes.
Good. I have no space. I have go to the next page. Then I'm just going to only take this part to the next page. What I have, what did I get before? I got before that the sine of alpha is what? Is x divided by 4. Am I correct? X divided by 4. Okay. And now, guys, everyone can see clearly what I'm writing?
Yes.
Okay. And now, we are at this stage. This stage, essentially, guys, is a kind of, you had the core of the onion, and you find in the core of the onion something magic. How this is going to happen. That's the recipe of how to cook. Imagine, what is your favorite food in China? Say a name. Rose?
Yes.
What is your favorite food in China?
Dumplings.
Dumplings. Imagine you want to cook a dumpling for the first time. You don't know how to cook it for the first time. You start with an onion. You cut the onion in half. You remove the core of the onion, and you see the recipe, the instruction how to make dumplings. And that's what's going to happen now. It was the core of the onion with the recipe of how to cook the dumpling. How to do that? We learned that for the trigonometric ratio, we have a geometric representation, a geometric interpretation. Sometimes we have the sine alpha of x over 4, but at the same time, we have a geometric representation. What is that representation? Either we can just use the unit circle, which I have done that most of the time. I draw a Cartesian frame, then I draw a circle, which its center is on the center of the Cartesian frame. It's my one type of geometric representation of this sign. The other one, which sometimes I used it before, not very rarely, is the time that we talked about a right triangle. And we learned that before when we talk about that, for example, how to solve a right triangle. You remember that lesson? By solving a right triangle, the right triangle means a triangle that one of its angle is 90 degrees. This right triangle is the second method of the geometrical representation of this trigonometric ratio. With this right triangle, I start from here and I assume the angle which I have is in that representation. I think one of the angles, either this or this, it doesn't matter. I choose alpha here, the alpha which is expressed there. You see that? I'm gonna take it here and I show that, okay, that's gonna be the same alpha. Okay. Based on the definition, guys, look at the magic. What's the magic now? With one single trigonometric ratio information, we can solve the entire triangle. I mean, knowing all the triangles and all the length. We have three angles, we have three lengths. By single trigonometric identity, we can get all this information or essentially solve this right triangle. If this is alpha, this is 90, how much is this angle?
90 minus alpha.
That's right. And based on the definition, then now we have every knowledge of all the angles. Alpha, 90 minus alpha, and 90. There are no other, I should say, angles. The other thing is the length. The definition of the sine of any angle means what? The ratio of the length, which is the opposite of the angle, divided by the hypotenuse. You remember that? It means that if the sine alpha is x over 4, x represents the length in front of the alpha, which means this. This is going to be the x. And 4 represents the hypotenuse of that angle, which is going to be this. Then 4 is this. You see, by one single trigonometric ratio, we got this information. But if you remember, we said that when we talk about solving a right triangle, also we mean that we find information of all its length. We have x, we have 4, we have one length which is missing. What is this length? What is the length of this length? This side, I mean.
Square root of 16 minus x whole.
That's right.
Square.
That's a Pythagorean theorem, Rose. That's right.
Yes.
It becomes 16. The length of this squared becomes 4 to the power 2 becomes 16. Minus this side length squared becomes x squared. Right? And now, everyone is good so far? Philip and Gloria?
Yes.
Yes.
Great. And now, if I'm at this stage, what I was planning to do, I'm just going to go back to this. I called the core of the onion, which rose by knife, put that on the table, and Gloria asked, what is that? We call that alpha. Alpha is inverse of the sine of x over 4. If I put alpha in here, the expression becomes the secant of the alpha. Am I right? Imagine the whole core is alpha. Then we talk about the secant of the alpha. Am I right?
Yes.
Okay. And now, I'm just going to use now what is going to be the secant of the alpha, which it takes only 2 seconds to finish it. Secant of the alpha. What is the definition of the secant of the alpha, guys?
1 divided by cosine x alpha.
That's so true. If I have alpha here in this right triangle, this is a geometric representation of my trigonometric ratio. The secant of any angle is essentially the inverse of its cosine. But what is a cosine? How do you define in the right triangle as you learned it before? Let me write this like this. It becomes 1 here. And for the, what time is it now? Okay, you need only 1 minute to finish it. I'm just going to write it by this color. Okay, for the cosine of the alpha, we learned cosine of any angle. If you remember that, it's the adjacent side divided by the hypotenuse. The sine was the opposite side divided by the hypotenuse. For the cosine of alpha, we say that the adjacent side divided by the hypotenuse. What is the adjacent? Square root of 16 minus x2 divided by what? The hypotenuse. What is the hypotenuse?
4.
4. Fantastic. Then I can simplify that. You know, far by far, close by close. Then I get the secant of the x becomes this very easy expression. This one, 4 goes on the top. And this square root goes at the bottom. 16 minus x squared. Is it correct?
Yes.
That's right. Any questions, guys?
No.
No? Then, in order to finish, guys, you see that this mixed model of the secant of the sine inverse of x over 4, it is only represented by this algebraic equation. Look at this. I'm going to write this one here, and we finish the session by that, and you see the beauty of these functions. Our function was what? F of x was a secant of what? Of sine inverse. Am I correct? X divided by 4. Is it correct? Our function was this. Let me double check. That's right. The function was that. But at the end, you see that f of x is equal to what? Is equal to this expression, which is 4 divided by 16 minus x squared. And that's the beauty of this rule, that you use the onion rule for a mixed models of forward, computation of forward and backward trigonometric function. A very easy to understand trigonometric function is represented by a simple algebraic function which has no trigonometric ratio whatsoever in it. And it's now very easy to analyze it, to say what is a domain, what is the range. For example, if I had asked you before, what is the domain of this function, guys? Was it easy to find it? No, honestly, no. But with this form, you can find the domain that it can be any x except that it should be not -4 or +4, that it doesn't take the denominator goes to 0 then. And also one critical thing, that it should be also positive, that gives you the second condition. Then you see that the beauty is this. One function with one single algebraic equation. Isn't that beautiful?
Yes.
Yeah, I really like that. Wow. Okay. Any questions, guys? Rose and Gloria?
No.
No questions? How about Chen Chen?
No.
How about Gloria?
No.
No? Okay, guys. If you have no questions, we have the class essentially is done. The only thing which is left from you to do is that please go to the comment which I have put on the course website. At the comment section under the course criteria, the learning success goals, write the comments as what did you learn today then. Please do that and you're done with the day then. I can say goodbye now to you, and you please do that and just go there and put the comment there. And if you have no question, we finish the session. Rose, any questions?
No.
Gloria, any questions?
No.
Thank you. And Rose, by the way, I sent you the questions for the math competition today to your Schoology message then by 4 p.m.
Yes. Okay.
Thank you and good luck with it. And we just work together in case if you have any questions.
Yes.
Awesome. Thanks. Gloria, do you want to go to the math challenge?
Okay.
You want to do that?
Yes.
Are you sure? It's too much work.
It's okay.
It's okay. Then please
Yes.
stay in touch. Stay in touch with Gloria, with Rose. Both of you have your phone numbers?
Sorry, what?
Do you have your information contacts?
Yes, we have. Oh, we chat.
Okay, then please work together. And I'm just going to send the questions to Rose today. Then you work together and we stay in touch to solve all the questions then. Okay?
Okay.
Okay. And Gloria, in case if you change your mind, because there's lots of competition, if you change your mind, let us know that. Okay?
Okay. Okay.
Okay. Guys, thank you very much. And I see you all Monday then. Then Rose, please stay tuned for the questions for the math competition then. Okay?
Okay.
Awesome. Thank you and see you all later then. Have a nice day.
Bye.
Goodbye, everyone.
Bye.
Bye, Gloria. Bye, Rose.